So yes, we'll begin again. We are talking about the derivatives of a complex function, and inevitably that leads to some discussion about the limits of a complex function. Now, in case of a scalar function, we say this ensures that we have a unique derivative. You will find most of this whatever I'm saying now trivial. Now, as we move to complex functions, what happens? We are looking at z is equal to a plus ib. Now, why is this necessary? Because for a scalar function, we have again the luxury of letting x varying along this line. We have a point A, this is the neighborhood of A, and this, although I am showing this by a circle, actually this is it. So this is minus h, A minus h, and A plus h. We are moving within these boundaries, and we are checking for the existence of derivatives and also the uniqueness of the derivative. What happens when we have, look at the complex plane. We have imaginary, we have real, and we have this point AB, and this is the domain. So I might choose to move this way, I might choose to move this way, I might choose to move this way, I might choose to move this way. There are multiple ways, infinite ways in which I may move. I may even choose to go this way, a peculiar path. So this definition of limit itself has to be kind of reformulated, and we also have to think of how to redefine this business of uniqueness of derivatives. So we have a unique derivative when, irrespective of the direction of approach, we get the same result. And this is something that we will be utilizing when we deal with certain aspects of contour integration. Now, how do we define fz? Fz actually has two parts. A real part, which again is the function of xy, plus an imaginary part, v, which again is a function of xy. And z is equal to our x plus iy. Excuse me. So we have something called Green's theorem. Which states that when we are integrating over a contour, and we have something like this, two functions phi and xi, this can be expressed as a double integral where the double integral is actually the domain enclosed by this contour. So to understand this, we will look at these individual derivatives. And we proceed along the real axis. That is, here delta y will be permanently set to 0, whereas my delta z will be only therefore consisting of delta x. So my f dash z will effectively be limit of delta x tends to 0 and this will give me thereafter we will consider along the imaginary axis only. That is, this time we'll have my delta z whereas my delta x will be permanently set to 0. So you do the same thing sorry, this will be delta y. Now the thing is, I have made a small mistake here, which is actually I will be incrementing, so far as the z is concerned, here what is z plus delta z? And here what is z plus delta z? Here it will be x plus I y plus delta y, which means I should be having an I out here when I actually am setting delta z equal to 0. Because of that, when I write down the derivative, I will be getting and hence I will be getting del u by del y with an I in front, whereas here the i's will cancel out and I will be getting del v by del y only. So now comes that business of uniqueness. Limits must lead to same result. And therefore, if you compare real to real and imaginary to imaginary, you will be getting del u by del x and these are, anyone recalls this? What are these called? You have done your maths, you have done your fluid mechanics. Anyone?
These are the stream functions and the potential lines.
Close, close, very close.
So the
Cauchy-Euler equation.
Two famous scientists.
The Cauchy-Euler equation.
Cauchy-Riemann. These are the Cauchy-Riemann equations. So we will next use these things that we have cooked up to study the behavior over contours. And what kind of function will we study? We will be focusing on analytic functions. Their properties are they are single valued, and have unique derivatives. Which means that Cauchy-Riemann equation will hold true for them. So we have excuse me. So this will break up into u dx plus I u dy plus v dx. And if you apply Green's theorem, then this will become this is what you have from Cauchy-Riemann, and this is your Green's theorem. So we'll be having 0 plus I0 equal to 0. And this fz dz of an analytic function over a closed contour being equal to 0, this is again another contribution of Cauchy, and we call this as Cauchy's theorem. These are people like Cauchy, Euler, etc. I mean, it's often very safe to kind of specifically mention when a theorem has a name, which area are we talking of, because most of these chaps have contributions in multiple fields. For instance, we have Galileo's theorem in mechanics itself, which tells us why if you just scale up a fly to the size of an elephant, the fly will collapse under its own weight. But these people have contributed to multiple fields, and this is one of them. So now comes the extension of this theorem. So this is the imaginary axis, my real axis, and I have a point A. And this is my path. Sorry there. So we are now considering a domain in other words, how to deal with poles, and this is where we get to understand how this has relevance to the Nyquist plot, because our Nyquist contour, well, what do we do when we are dealing with poles poles along the contour that we are going to take? Or if there are poles within that contour then and zeros within that contour, what will they be doing? So we have the following paths to be taken. One is, if this A were not there, then we would be following a path C, which would just begin and end here. Okay? So this would have been our C. But because A is present, we are splitting C into two paths. We are going to a point B out here in the neighborhood of this point B. We are taking a sharp turn, moving this way, and then taking a small circular path C1 and coming back to our original path again this way. So my integral fz dz now becomes if we consider the fact that the directions are changing, so we will be having one integration with a negative sign over the domain C, over the contour C rather, and then another over AB, over BA, okay, and what is now left? This whole integral, overall this should satisfy Cauchy's theorem because we are not including A. Okay, so on the other side, therefore it should come equal to 0. So on the other side, I will be left with my C0. So effectively, actually what we are saying is that this, we may change the sign, but this is overall equal to 0. This I can take as negative or positive, I mean, like, it really doesn't matter. So I'll keep it as positive. So this has to be 0 because this is a path. Overall the path is not something that involves an non-analytic point. So this whole domain is actually, this path does not involve a pole. So the overall integral should come out to be equal to 0, and these two should cancel out, and therefore we should be getting this fz dz should simply come out as equal to this integral only. And when it comes to this integral, we will consider so when we consider a function like this, then we have seen that, therefore it means that we can consider a circle, small circle, and we can put and this will become as I put epsilon tending to 0, then this will become simply equal to z is equal to, so yeah, there will be a small, so my dz will be equal to so this will be d theta into so this and this will cancel out, and I will be getting So as epsilon tends to 0, this will simply see epsilon does not play any role in changing Z0. It changes Z. So when epsilon becomes 0, then Fz0 is simply going to come out. And we are going to get also the I outside the integral, and this d theta will contribute 2 pi. So every pole contributes at Z0, contributes for that this kind of a contour integral. It contributes 2 pi I f of Z0. Such as Z0 means this Fz at the top is a nice function, no analyticity, and this is the only analyticity present. It is showing up as Z minus Z0 in the denominator. And an extension of this is the residue theorem, which essentially states that what do we have? We have this integral of Fz dz this Fz is not the same as this. This is where we have separated out the pole. Okay? So we will have if we write this in the form and do the same stuff, then we should be able to write this as Now, important point is I think again you may have studied a little bit of this. Maybe during your classes on Laplace transform, because there also actually if you want to find out the Laplace transform without going into the business of factorization, you need this. So finally, armed with these tools of mathematics, we come to something called principle of argument. This is where we are coming close to Nyquist. So we have our Fz, and we have Z minus P1 Z minus P2 to the power beta 2, and finally Z minus, oh this will be Pn, sorry. So we are considering not only poles and zeros but also poles and zeros with multiplicity. And multiplied by some Fz, where this poles and zero part is not there. So now if we take the log and take derivatives.
So shouldn't that capital F be essentially a constant?
Not necessarily. But these are the poles and zeros of the function, and we'll assume that in our domain this Fz is something that does not have poles and zeros within our domain. So that is a part that we are separating out. In some domain it may, but in our domain of operation it does not. So if we take logs on both sides, then what will we get? and all of these excuse me. So this is what we get by logarithmic differentiation. So now if we do the contour integration, see what we are going to get. This will be the integration of now this is, as we said, this is a nice function. This does not have any problems over C. So this part will become equal to 0. These, all of them have individual, clearly defined poles. The zeros are also actually poles in this form. 1 by z minus zi. So that means this 1 by z minus zi has a pole at zi. So what will I get? Each of these will contribute 2 pi I all right. I am writing a j here to avoid confusion, that j is equal to root over minus 1. And similarly we will have sorry, it's better to call this a 0 to avoid confusion for now. And so what do we get at the end of this all? We should be getting 2 pi I z minus p total number of zeros including multiplicities that means if it is a multiple 0 you have z minus 5 square, then that counts as 2. So we are getting close to what is known as the finish of this principle of argument. So our summary is Just a moment. So here is another property of complex numbers and the log of complex numbers. So what can we express this as? This is log of fz, and this is going to come out as, unlike scalar functions, this will come out as a modulus part and this has to be evaluated over the domain C. That is why this so-called, this name comes up, the principle of argument. This part, because if you are moving over a closed domain, and if you are a little bit confused about this, think of this part that a complex number and hence a complex function also can be expressed in the form, just as a complex number can be expressed in the form r e to the power I theta, a complex function can also have a polar form, magnitude into e to the power argument form, where the magnitude is a function and the argument is also a function of z. So when you take the log of a complex number, unlike a scalar number, then it actually has two parts, and the magnitude part, if you are moving over a closed contour, if you integrate, then you are coming back to the beginning, this is going to become equal to 0. But this part being an angle, this is not going to be 0, and this is the non-zero part that we are seeing that is coming out. So this is the part that we evaluate over the domain C. Okay? So we now come to this basic fact and that is the number of encirclements gives me of the origin. If you are looking at a function fz, then that gives me the number of the difference between the number of z's, the zeros and poles in the domain encircled by the contour that I am considering. I have a contour that contains z zeros and p poles of a function fz, and what we looked at just by kind of experimentation, this is the mathematical proof of that the z minus p will be equal to the number of encirclements of that function plotted in the complex plane of the origin or the point 0, 0. And when it is 1 plus fz, well, it will be the number of encirclements of the point minus 1, 0. So this is the mathematical proof of what we have already done, what we have visualized physically. Now, how does this help? This helps in the sense that, see, you look at GS. GS is our own system. We know all its ins and outs. That is poles and zeros. So we are not worried about GS alone, because most of the times, let us understand this very clearly, that we deal with systems which are, to start off with, which are good systems. We are not dealing with, the jinnah in a bottle, and we are not opening up that bottle out of curiosity. Our jinnah, if at all it is a jinnah, it is still enclosed in a bottle and given to us. And whatever we will do, we will be doing on the bottle, not freeing the jinnah. So even if we have an unstable system somehow to start off with, we make it stable and then we deal with it. So our starting, most of the cases that we will deal with, we will have systems which are good systems to start off with. And we will have a fairly good idea, because that system has been with us for a long time and we have studied it. So we will know its poles and zeros. The manufacturer so that means this GS we can write as, we know it as factored into poles and zeros, okay? HS we know as but when we give a feedback, that is when we have Excuse me. And when we set this equal to 0, we get dg dh So we are actually looking at now see what is the advantage that we are now getting. For ease of understanding, take k is equal to 0 is equal to 1. So you have 1 plus GSHS, all right? So you can, from your own experience, you know G completely. You go to a shopkeeper and it sells you, an honest shopkeeper sells you an HS for your control, giving you the complete details. So that means both for the G into H, you know how to factorize its numerator, you know how to factorize its denominator. So for this GH, you know the zeros and the poles. And what does this Nyquist criteria give you? Choose a proper contour, and Nyquist criteria tells you, by just looking at the plot of GH along that contour, you can figure out the difference between Z minus P. This does not sound much because you already know Z minus P. But what does sound like $1 million? That you can find out the number of roots of 1 plus G into H by simply plotting GH on the complex plane and noting the number of encirclements of the point minus 1, 0. This is that way a very brilliant discovery. GH completely known to us, zeros and poles of GH completely known to us. All we have to do is choose a suitable contour. And what is that suitable contour? The bad roots are in the right hand plane. So we simply have to choose again, as we see, circle of infinite radius plus its infinite diameter as our contour. So if we go along this contour, and if 1 plus GSHS has any roots out here, 1 plus GSHS equal to 0 has any roots on this side, we will immediately be able to detect it by checking this is the plot of GSHS. We can immediately find out how many times does the root lie by checking this. How many times does this whole thing, this plot, move in a circle, not circle, but how many times it completes the encirclement of this -1, 0 as my S moves along this. And there are further advantages in the fact that, you know, over this path, what is my Z? My Z is infinity e to the power I theta. And over this, it is simply some I omega. So this part, because it is infinity, you will find that we won't often need to actually check the behavior of this part when we are actually plotting a function GSHS. We will often not need to bother about this part, and we will need to focus mainly on this part, and this part is easily doable, and we can therefore generate important part of the Nyquist plot pretty easily using a computer or even by hand and check for this. And as you can see from here, what we are bothered about particularly is if we can plot something close to the -1, 0 part and not really bothered that much about infinities, we are still done. We are going to get the answer that we require. So in the next lecture, I will show how this can be done and how we can solve some practical problems using this. My final lectures will focus on designing certain stuff called compensators involving both root locus and a little bit of Nyquist as well. There are some other parts also, like we have something called M circles and N circles on the complex plane that are also a part of Nyquist circle studies, Nyquist plot studies. I will finally conclude by saying that there is yet another way of getting a very Nyquist-like plot. Here, what have we plotted? We have plotted the real and imaginary part of FSGS on the complex plane. A complex quantity can also be plotted on a piece of paper in another way, which is by plotting its magnitude and argument. So when we do that kind of a plot for FSGS, then we call it as a Nichols plot to keep the plot compact. When it comes to the magnitude, we often use the log of magnitude. That is more or less the standard practice. So we can use either of these two Nyquist plots or Nichols plots. In fact, Nichols plot is more popular among practicing engineers to design our systems once we apply feedback control. So I'll conclude my lecture here on Monday with our theoretical baggage more or less complete. We will start working on some implementations of such theories.